dynamic crack initiation. So I added the first slide after Dominic's presentation yesterday. We recalled Ashing points of view about finite fracture mechanics. And so the Ashing, 1996, was describing finite fracture mechanics as the spontaneous crack formation. And he said that it was not possible nor of interest to follow the development of the crack during the nucleation step. So I was a bit upset, because here it's me, 2022, and I will precisely, the topic of my talk is precisely to talk about this, to try to convince you that it is possible, and to my mind it is interesting to try to follow the history of crack during the nucleation. Okay, so now why doing this? Let's talk a bit about this experiment, but for them who were there yesterday, you already see them in Rafael Esteves' presentation. So we did some experiments dedicated to the crack nucleation process. So rhombus hole specimen with this kind of shape for the hole, under compression, and then what you see in this kind of... Oh, let's try again, no? Okay.
Maybe, yeah.
So what we see here is that we have an unstable propagation phase at initiation. So we have a spontaneous crack formation on a finite distance over a really short time. So actually, what it is a dynamic phenomenon. We create a large crack surface into a very small amount of time. So the idea was to try to describe this into the couple criteria. So let's first have a look at what exists in the literature regarding dynamic and the couple criteria. So to the best of my knowledge, the first work concerning dynamic was a work by Lepavich and the co-workers, who tried to modify the classical stress criterion by making the tensile strength and the shear strength depending on the loading rate. So they did these experiments on interfaces. They identified this parameter of some set of experiments, and then they could do some prediction depending on the loading rate. Second work, which is actually not really dedicated to dynamics for the couple criterion, it's rather a work about cohesive zone model, but I found this interesting discussion about the fact that when a crack initiates with the couple criterion, we have the incremental energy release rate equal to GC, and then the energy release rate is larger than GC, because we consider the quasi-static energy release rate. So their assumption is to say that actually if we consider the dynamic energy release rate, and we use the relation given by Freund, that is found for analytically for a crack, a semi-infinite crack in infinite media, then they were able to try to estimate what is the crack velocity during the nucleation step. And then third work, I will just describe it because there was a really nice talk yesterday by Arturo. So this was the proposition of extension of FFM to dynamic. So these three works deal with dynamics, but actually the cracking kinetics, the description of the crack formation process is not accounted for in these three works. And this is exactly what we wanted to propose in the present work. Okay, so what we observe experimentally, we load the material, there is no crack, and then spontaneously, abruptly, there is a crack forming over a given length. So when we do the classical quasi-static approach of the couple criterion, basically what we do is we load. So here is time, but it could be understood as load. And there is no crack. Here is the crack length as a function of time or load. And at some point, okay, we have initiation over a given length, and then possible unstable crack propagation. The idea of this work was to try not to consider this anymore, but to really consider how the crack develops from 0 to LC. So now we are just considering that we load, there is no crack, and at some point the crack will nucleate, but following a certain velocity profile, so crack velocity as a function of time, or crack length as a function of time. So what do we need to add in the classical couple criterion to take it into account? Well, we need to describe this. So we need a crack velocity profile first. Of course, we need to add the material density because now we are going to do dynamic calculation. And we need to slightly change the couple criterion formulation and still retrieving the classical quasi-static formulation when the crack is propagating or is nucleating really slow. Okay? So let's go ahead. In this presentation, I'll only focus on quasi-static loading. Okay? So we consider the dynamic crack nucleation, but under quasi-static loading. So if we have a look at the stress criterion, it changes nothing because everything with the stress criterion is evaluated prior to the crack nucleation. Now what is going to change is the energy criterion. So let's start with the classical energy balance that we do for the quasi-static approach of the couple criterion. So you have to do this energy balance, so the sum of kinetic, potential, energy, crack surface, creation energy, maybe the energy that you may dissipate by plasticity or damage also, must be equal to the variation of the external work force. Taking this, we can define the incremental energy release rate in this way, and usually what we say is, when we are quasi-static, this term, for a quasi-static loading, there is a creation of kinetic energy. So this term is positive, and usually what we say is, okay, since this term is positive, we can just get this inequality. So incremental G must be larger than GC. Okay? Now if we consider the dynamic approach, we are no longer going to suppose that it is positive, but we are going to compute directly the variation in kinetic energy. And then, so here there is a small mistake, it should be equal, but the energy condition will be incremental G is equal to GC. Okay? So basically we have finally the exact same formulation as we had before for the quasi-static formulation, except that we are going to compute this term and see what is the influence when the crack propagates. So in this presentation I won't take into account non-linearities induced by plasticity or damage, but it's possible to do sorry, with some more difficulty. So the new ingredients in the couple criterion, we need this crack velocity profile. So we need to describe what is the crack length variation as a function of time between 0 and between the initiation length, LC. Then we need to compute the sorry. We need to compute the incremental energy release rate. And in the incremental energy release rate, okay. Then we have to compute this new term, the kinetic energy, and of course everything depends both on the crack velocity profile that we input and on the loading. Okay? So for the implementation, we are just going as usual to unbutton node following the crack path that we prescribed and following this crack velocity profile. Sorry. Yes, just to mention, we can also consider that GC may depend on also some feature like the crack velocity, but just for this presentation of today, we keep GC as a constant. I will skip this because I think I won't have time to discuss it. And so let's go to the application. We are going to apply the dynamic couple criterion to this case, so tensile test on PMMA specimen with a hole, with different hole size. It's experiments that were done by Giali and co-workers, and what they found, so here you have the black dots that are the experiments, and here you have the prediction by the couple criterion. So they identified the parameter GC sigma C on other tests, plane specimen under tension and I think notch bending specimen. So they add this parameter, and using the couple criterion, they show that they could not retrieve the experimental points. Sorry. Okay, the couple criterion was underestimated. Okay, the experimental points. So we wanted to try to apply the dynamic couple criterion to these experiments. So let's go ahead. And let's see what is the influence of taking into account a certain velocity profile on the result. So to compute incremental G, remember that we need to compute the potential the potential energy and the kinetic energy. So when we increase the crack velocity, what happens? In dashed line here you have the quasi-static solution, and then the different curves correspond to different crack velocity. So when we increase the crack velocity, we are going to decrease the potential energy that is released when the crack advances. On the one hand, and on the other hand, we are going to increase here the variation of kinetic energy that is created. Okay, so the faster the crack, the larger the kinetic energy creation. And since G incremental is this minus this, when we increase the crack velocity during the initiation phase, then we are going to decrease incremental G. So at the end, when we increase the crack velocity, we decrease incremental energy release rate, and then we are going to increase the loading that we need to initiate to fulfill the energy criteria. And then we are going also to increase the initiation length. Okay? So finally, if we have a look at the remote stress variation as a function of the hole radius. So if we consider the quasi-static application, we retrieve the same result as I showed before by Javi. And then if we increase the crack velocity, so for very small crack velocities, actually we have something that is really similar to the quasi-static solution. So we retrieve, when the crack goes very slow, the quasi-static solution. And if we increase the velocity, we see that we must increase the remote stress at crack initiation. And here you see that if we consider a crack velocity between something like 5 and 700 meters per second, then we retrieve a good agreement with experiments. So now this has to be confirmed against experimental measurement of the crack velocity profile. And so I just took some recent results in the literature by a co-author of Vlado, who did exactly the same experiments on other kind of PMMA, and they recorded the crack initiation and propagation with a rapid camera. And so there was a scattering in the crack velocity, but the average crack velocities were in the other magnitude of what we found here. Okay, thanks, and sorry for the voice.
Question?
Thanks for your presentation.
Quick answer.
Slowly, if you can, yeah. When you change the crack velocity, how it is related to the material property? Normally it should be related to the speed of sound, right? Bulk modulus,
Yeah,
or density square root.
Actually, it's related to Rayleigh velocity.
Yeah.
So, experimentally, you see that if the crack velocity is larger than 0.6 or something like this times the Rayleigh velocity,
Yeah.
the crack is going to branch. Okay.
Yes.
And then here, when we evaluate what is the influence of crack velocity, we vary this between 0 and something like 0.6 the Rayleigh
within that.
But we can do even numerically, we can do even 0.8 or 0.9 times the Rayleigh velocity. The thing is that if you approach the Rayleigh velocity, the incremental G is 0. It approaches 0.
Mm.
So yeah.
Thank you.
Still one question? It seems to me that dynamic effects enter in two ways. First, you have to replace the equations of elastostatics by elastodynamics. If you've done that, this is what modifies the expression of the energy release rate. And you may also have an influence of time, some kind of viscous effects in the constitutive behavior. It seems to me that clearly what you've done is that you have completely neglected that, because you said that you neglect the dissipated energy by processes other than the crack advance, and you assume that GC does not depend on V. So it seems to me that you assume that the processes which lead to fracture are, well, not elastic, but independent of time.
Yeah, sure. All these parts is completely neglected. So we would have to think about how to. I think we could implement that by taking into account time-dependent behavior for the material, for instance, but it would require taking into account also in the energy balance. Then, no.
Yes, but I think you must have an idea about the presence of viscous effects in your continuous law. Or they are none. So it would be a good argument in favor of what you're doing.
Yeah.
Thanks again to